So the next topic is called as a clock skew and clock jitter. What is clock skew? Nothing but it is the difference between the two appearance of the two clock signals. Suppose if you take the two flip-flops here, and whenever you are passing the clock will be appear to the two clock signal, two flip-flops at different periods, and this difference is called as a skew. This difference is called as a skew here, and skew can be defined as the instantaneous difference between the reading of any two clocks is called their skew here. Okay? Nothing but if you take the one small circuit here and you are applying the same clock signal for different circuits, some for different chips here. At that time, for one chip, the clock will be processed early. For the next chip, the clock will be processed some slow here. Nothing but somewhat delay. And the difference between these two, nothing but appearing the clock signal for the one chip and appearing of the clock signal for the second chip, and it is called as the clock skew here. Okay. Now let us take the one example. Suppose you are taking the one destination comma source here, and when the clock is appearing at the time of TCI for the destination and TCJ for the source register, and the clock source skew can be defined as it is a difference between these two signals. Okay. Now we can explain with respect to one diagram here, and it is a one small diagram, and it is a large chip here, large IC, so integrated chip, and in this one, we are using some flip-flops or any registers, whatever it may be. Okay. And A comma B, these are the two registers or two flip-flops here, and whenever you are applying the same clock signal, whenever you are applying the same clock signal, whenever you are applying the same clock signal, one clock appears to the A signal early and B later because of it has to travel somewhat extra distance here. So while it is traveling for the extra distance, so it takes a somewhat extra time here, and this extra time is called as a skew. So it is called as a skew here, and here it is for A register, it is for the B register here. Okay. Now if you take these difference, okay, and it is a difference between the TCI comma TCJ, which is called as the clock skew. So there is a somewhat drawback because of clock skew, and there are some advantages, but when compared to these two, the drawbacks are more here. So we are going to reduce the clock skew here. Okay. So let us come to the next same topic, clock skew. So here mainly we are taking the two types of clock skews here. One is called a negative skew, next one is called a positive skew. Okay. So what is the positive skew? When the transmitting register receives a signal earlier than receiving register, it is called as a positive skew. What is the positive skew number? When the transmitting signal receives the clock tick, nothing but very early when compared to the receiving register, it is called as a positive here. What about the negative? Negative is nothing but whenever the receiving register gets the clock tick early when compared to the sending register, nothing but transmitting register, and it is called as a negative skew here. Okay, it is a main difference between these two. So it is a positive skew and it is called as a negative skew. And so there is a zero clock skew here. What is the zero clock skew number? If the receiving signal and also receiver register comma transmitting register receives the clock signal without any delay, without any delay or any prior, and it is called as a zero clock skew. Nothing but the two registers are receiving the signal at the same time, and it is called as a zero clock skew here. Okay, and it is called as a ideal condition. But ideally, there is no chip will be designed. So for that purpose, there is a small clock skew when compared to the ideal. Practically, there is a some clock skew here. Okay. And here, so there is another definition for the, and there is another small word that is called clock jitter. What is the difference between the skew comma jitter? In the skew, the period of the signal will be same, nothing but the positive half cycle, negative half cycle will be in ideal condition. The positive half cycle comma negative half cycle will be, what is it, now explain. So the positive half cycle comma negative half cycle will be same in the skew, but in the jitter, the positive, the time period, nothing but the positive half cycle comma negative half cycle will be varies here. Nothing but these are called as a non-periodic. So it is a main, you have to remember this one. So nothing but it is called as a non-periodic. Suppose if you take the this one, it is called as a non-periodic. But whenever you are taking a skew, it is a periodic. So it is the periodic here. Nothing but, so here, so in the first class, it is a jitter here. So here the negative half cycle is going on reducing, and it is also reducing here. But here, so it is again increasing, and due to the increasing comma reducing, again here the two will be same here. Nothing but at some places the negative clock cycle is reducing, at some places the negative clock cycle is going on increasing, and at some places the two signals will be same here. And in the clock skew, wherever you take the any position, the second clock will be either forward or delay or prior. That will be for everyone, for every position here. Suppose let us take the previous slide. Let us take the previous slide here. It is a clock skew here, and here it is a difference here. So we are taking the, and it is a difference here. Okay, it is a difference, and this difference will be maintained at every clock cycle. So at every clock cycle it will be somewhat delayed, and this length will not be varies. This length or this length will not be varies. But whenever you are coming to the jitter, whenever you are coming to the jitter, so whenever you are coming to the jitter, so the clock, the period will be varies here. So the period will be varies. At the same time, sometimes the second signal will be forward prior, or sometimes the second signal will be some delay here. Okay. Now I will explain the what is the TCA comma TC here. What is the TCA comma TCJ? What is the TCA number? The time at which the clock signal appears to the A register, and TCAJ nothing but the time at which the clock signal is appearing to the B register. So it is a A register and it is a B register. And here, suppose it is appearing at the 20 nanoseconds, but here we are taking the 30 nanoseconds. What is the difference between these two times? Remember, 30 minus 20 nothing but 10 nanoseconds of the delay. There is a difference of the 10 nanoseconds of the delay, and this 10 nanoseconds is called as a clock skew, and this 10 nanoseconds is called as a clock skew. But whenever you are coming to the jitter, the 10 nanoseconds will not be same for the each every clock here, and it will be some 5 nanoseconds, it will be 10 nanoseconds, it will be 25 nanoseconds, and it will be 0 nanoseconds at every position. So the delay will be changes, nothing but it is called as a clock jitter. And next come to the clock latency. Clock latency is nothing but it is the time taken to reach the sync point comma source point. So I will explain the what is the sync point comma source point in the next slide here. Just to remember that, so it is a difference between the clock reaching to the sync point comma source point here. Okay. So here we are taking the two networks, nothing but one is called source network comma sync network here. And so the source latency is defined as the delay between the clock wave generation to the definition point. And source next sync latency in the embed, it is a difference between the definition point to sync point. Sorry, it is wrong here. So it is not source latency, it is called sync latency. Okay, and it is called as a sync latency. Okay, now come to the now what is the definition point? Suppose it is a clock source. Suppose you are using the some crystal oscillator, and the crystal oscillator is called as a clock source here. The crystal oscillator. From crystal oscillator to you are passing the signal to any some register. Nothing but so you can you are designing the one adder by using the registers, or if you are designing the some counters, then we are using the and it is called as a network latency. It is called a network here, and it is called as a some point. What is a point in the embed? It is a definition point here. What is the source latency in the embed? The clock is passing from the crystal to one particular point, nothing but definition point, and it is called as a source latency. Okay, and it is called as a source latency. Okay, now after the definition point, again it has to reach the some network, and this is called as a network latency here. So it is called a source latency, it is called a network latency, and it is called a source of the clock here, and it is called a definition point, and it is called a network here. Now, so these are the main clock skew, clock jitter, clock latency. So clock skew, nothing but so the delay will be constant for every pre-delay. What is the clock jitter in number? It will be varies. So sometimes it will be delay, sometimes it will be prior. And next clock latency, nothing but it is also called as a delay. So the delay between the source point to network point here. And so how can you reduce these things? Now you can see the next slide here. Clock routing. So we can use the clock routing to reduce the skew or delays. So we have to reduce the skew comma delays by using the clock routines here. In the clock routines, mainly we are in the two methods. Those are the called as the clock tree routing, H tree routing. Clock tree routing language. So we are using the buffers in the tree model. So we are using the buffers into the tree model. In H tree, we are using the H networks. So we are using the H networks here. So it is called as the distribution of the clock here. What is the distribution in nothing but? What is the distribution in number? You are passing the clock from one point to so many points. Suppose nothing but it is a crystal oscillator, and you are passing the clock from the crystal oscillator to some so many flip-flops here, and the crystal oscillator is called as a source point, and the so many flip-flops or registers are in some networks, and these are called as the destination points here. And you are passing the only one clock signal, you are distributing this clock signal to the so many circuits here. and there is a possibility to get the latency or some delay here. How can you reduce the latency or delay in the embed? By using the clock tree routing. What is the clock tree routing in the embed? We are using the so many buffers. What is the use of the buffer in the embed? We will restore the signal. While you are restoring the signal, then we can easily reduce the skews or latencies here. While you are restoring the signals, so you can easily reduce the skews comma latencies here. And so it is a one type of technique to reduce the clock delay. Now we are going to the, so we can explain by using a small diagram here, and it is called as the clock tree network, and it is called a source point here. It is called a source point. From source point to, you are distributing the same clock for so many flip-flops here, and these are called as the so many flip-flops, and you are distributing the same clock here. Suppose if you use the only wire, then there is a possibility to get the latency here. So for that purpose, we are using the buffers. So the buffers will restore the data here. At that time, the latency will be reduces here. Okay. Now come to the hex tree. What is the hex tree embed? You are passing the signal from source to some other points here by using hex model, and it is called as a hex model. And so it is called as source here, and you are passing the signal for the some points. Nothing but here you can pass the clock signal for the 4 circuits here, and if you extend the network like this, and here you are applying the clock here, and you can pass the signal for 4 into 4 nothing but 16 networks. So you pass the same clock signal for the 16 networks without any delay here. And so it is a head of the structure to pass the signal, and here to pass the signal. Okay. Now power distribution. What is the power distribution in embed? You are distributing the power to uh, some internal circuits here. How you can, so here mainly we are using the two methods. One is called as a one metal routing, next one is called as a two metal routing. What is the one metal routing in embed? You are using the only single metal for all internal structure, and it is called the one metal routing. But the two metal routing member, you are using the two types of metals, and one for the source comma one for the source, and remaining metal for the some internal circuit here. Okay, and it is called as a, and it is called as a two metal. So here, one metal, it is called as a one metal, which is used for the VDD, and same metal is used for the VSS, and metal 2 for the internal structures. Nothing but you can use the some extra connections here, and it is called as a power distribution. So these are the main topics we discuss today here. Okay. So hope you understood the concepts of the clock skew, clock jitter, clock latency, and how you are reducing the clock skew by using two methods. Those are called as a clock tree distribution, comma H tree distribution. So thank you.